Hello, my name is Clarice Hernandez Santana. I would like to give you a brief presentation of this poster, entitled Synthesis of Mixed Ferrite Nanocomposites Using the Sol-Gel Method Assisted by Autocombustion, with Potential Application in Biomedical Properties, within the context of the 32nd International Materials Research Congress held in Cancun. As you know, ferrites are a class of compounds of iron oxides and other transition metals. Ferrites, especially those replaced with rare earth elements, have been of great interest in materials science due to their diverse applications, ranging from data storage technology to medicine. These ferromagnetic oxides, with a structure analogous to the Ab2O4 spinel, exhibit ferromagnetic behavior derived from interactions, mediated by oxyunions, between divalent and trivalent cations. The incorporation of rare earth elements in ferrites improves their magnetic and structural properties, making them ideal for biomedical applications such as hyperthermia in cancer treatment. Current research is focused on the synthesis and characterization of ferrite nanocomposites using the autocombustion-assisted sol-gel method to optimize their properties for clinical use. The sol-gel method combined with self-combustion consists of preparing two aqueous solutions, containing the metal nitrates, the fuel and the surfactant, of the two ferrites separately. All these reagents are weighed in stoichiometric quantities. These solutions are then mixed in a single beaker and subjected to conventional heating by continuous heating to cause volume reduction. This gel is transferred to an alumina crucible and placed in a muffle or furnace previously preheated to 600 degrees Celsius, when self-combustion occurs. After this time, a powdered product is obtained which is ground in an agate mortar to homogenize and then taken to characterization. This slide shows the results of the obtained sample's characterization. First of all, in the X-ray diffraction we can appreciate that all the diffractograms corresponding to each ferrite nanocomposite were obtained satisfactorily since all the signals coincide with the crystallographic planes of the standard form of a normal spinel structure, and there is no presence of impurities or secondary phases. Secondly, the results corresponding to infrared spectroscopy show that one of the intensity bands obtained corresponds to the characteristic band of the spinel structure, especially concerning the ferrites located between 400 and 600 cm-1, which is identified as the metal oxygen band of the octahedral and tetrahedral sites respectively. The diffuse reflectance UV spectra are also shown. You can observe that the absorption spectra of the samples showed significant UV visible absorption. The highest absorbance peak can be seen in the spectra wavelengths between 900 nanometers and 1200 nanometers. Diffuse reflectance spectroscopy is the method used to determine the bandgap energy, EG, of a powdered sample. From these data we can estimate the EG of the material using the Kubelka-Munk function. Using a talk plot and plotting Kubelka-Munk function versus photon energy, we are able to extrapolate the linear part of the graph to the x-axis and to obtain the value of the sample where it intercepts the EG value. All this analysis performed to estimate the EG of the nanocomposites confirms that they have direct semiconductor properties. The results analysis also shows the field emission scanning electron microscopy, FACE-M, micrographs of the nanocomposites. The images revealed that the morphology of the synthesized samples consisted of agglomerated grains with spherical shapes. The agglomeration in the micrographs may be due to the magnetic properties of the ferrite. The particle size distribution was also determined from the FACE-M micrographs using IMRC software, which provides average particle sizes of 21.5 nanometers. In addition, EDXS analysis and elemental mapping of the nanocomposites were performed and are presented in Figure 7. These analyses evidence the presence of all the elements of the nanocomposites, confirming the successful formation of the desired compositions and that the lowest percentages are those of the rare earths, which is what is expected. All this supports the effectiveness of the preparation procedure employed. Conclusions: the ferrite nanocomposites were synthesized using the sol-gel combustion method. The spinel crystal structure was confirmed by X-ray diffraction, XRD, with average crystal sizes ranging from 18.4 to 37.6 nanometers. Fourier transform infrared spectroscopy, FTIR, spectra showed vibrational bands characteristic of MO bonds. Field emission scanning electron microscopy, FACEM, images revealed a spherical morphology with particle sizes ranging from 14 to 26 nanometers. Energy dispersive X-ray spectroscopy, EDXS, analysis confirmed the presence of all elements, thus validating the experimental process. UV vis spectroscopy showed bandgap energy values between 1.31 and 1.48 electron volts, confirming the semiconducting nature of the samples.